Awesome. Welcome to the 55th episode of HYSKY Monthly. I can't believe this is our 55th episode, but it is indeed. And today we're so excited to have Bav Roy of Verne. We're going to learn about cryo-compressed hydrogen, and I'm super, super excited for this. Today's June 17th, 2024, and I'm the founder and CEO of HYSKY Society. My name's Danielle McLean. I think most of you know me, but if you don't, that's me. We're a small nonprofit. We formed in January of 2023, so we're just a year and a half old, and we're just so excited to be here. So before we jump into this, I'm going to have some little action items. Hopefully you guys shared your LinkedIn profile so we can all connect. I want to have you click this link. And if you have a LinkedIn, click the link and repost it. Just hit the little repost. It says repost if you're attending HYSKY Monthly with Bav Roy of Verne to learn about, it says Verne, I think I said Verde earlier. Excuse me for that, Bav. Cryo-compressed hydrogen. So go ahead and repost that. Just click the link and repost it. Let's see how many people reposted it. This helps our algorithm. So far, just me, me and Jim. I'll give you the link again. Just click it and repost it. It helps us hugely. It's the little things. I see people commenting. Oh, there has been 7 reposts. Okay, I was looking at the wrong thing. Okay, awesome. Thanks, guys. This episode of HYSKY Monthly is brought to you by Therm & Co. Therm & Co. adds the personal touch to project management, contract management, and supplier management from right here in Houston, Texas. They help small to medium-sized organizations with strategic technical project management to ensure that they're doing the right things to keep their projects aligned with their business goals, while balancing the project management triple constraint triangle of scope, cost, schedule. They also introduce quality, risk, and communication management to their projects. We personally at HYSKY use Therm & Co., so I highly recommend them. Love them. Next, the Vertical Flight Society. The Vertical Flight Society is the professional society dedicated to advancing vertical flight and electric flight technology. VFS held the world's first electric VTOL symposium in 2014, 10 years ago. So think about that. We're all learning about eVTOLs in the last couple of years. They were doing this 10 years ago. And they just held the world's largest eVTOL event in January, including a hydrogen session with HYSKY, HYSKY, and HYSKY. VFS is holding the 18th annual Electric Aircraft Symposium, July 20th through the 21st at Culver Family Welcome Center, University of Wisconsin, Oshkosh. And we'll talk more about that here in a minute. Let me grab you this link if you want to learn more about that event. And I will be there as well. Next, we have SoCalGas. SoCalGas is the largest gas distribution utility in the U.S., serving millions in Central and Southern California, and they're committed to achieving net zero greenhouse gas emissions by 2045. SoCalGas is leading the way with innovative hydrogen projects. These include the Angeles Link, which aims to create the largest green hydrogen infrastructure in the nation, and hydrogen blending initiatives that integrate hydrogen into natural gas systems to reduce emissions and improve air quality. So huge thanks to all of our sponsors. We wouldn't be here without you all. We appreciate everything that you do for us. All of these HYSKY Monthly webinars are free on our YouTube channel. So another ask I have for you is to click this link and subscribe to our YouTube channel. There is hundreds of hours of content on hydrogen, just about anything that you could want to know, from onboard hydrogen storage, producing hydrogen, the hydrogen hubs, the Inflation Reduction Act, all of the different types of aircraft. I think all of the hydrogen aircraft manufacturers and developers have talked on this channel as well. So there's just loads of content. Just about anything that you could want to learn is there, free of charge. All that we ask is you subscribe. So subscribe. All 54 episodes after today, 55 episodes are there. It's the largest collection. And again, it helps us keep our content free. Another way that we keep our content free is we have sponsors, which you just heard about. Our sponsors, Therm & Co., Vertical Flight Society, and SoCal Gas. So the sponsorship opportunities are you can do a monthly sponsorship for $1,200, and your logo goes on a webinar like this, which goes on, it's mentioned in the live, and then it also goes on our YouTube channel forever. So you have forever branding on our YouTube channel. You can do quarterly, which is 3 webinars, or annually, which goes on every single one of these webinars, 12 of them for the year. So please consider doing that. If you're interested in that, you can scan this QR code and that will take you to the sponsorship opportunities. And then this is just a flyer for that. So, okay, cool. So upcoming events, like I said, next up, we have the 18th annual Electric Aircraft Symposium. If you're going to Oshkosh already, I highly recommend attending this. It is Saturday and Sunday before the Oshkosh event. And I think I saw Mike Hirschberg on the webinar. Mike, if you are here, I know you said you were on vacation this week, I think, but if you're able to unmute and turn your camera on, you're welcome to come on and talk about this event.
Yeah, can you see me?
Yeah, we can. Hi.
Hi. I was standing on the balcony of my hotel, and you can see the beautiful mountains of the beautiful mountains of Vermont behind me. So yeah, if you're going to Oshkosh, this is going to be a great event. If you hadn't planned to go to Oshkosh, you should. This is the biggest AAM event there at the at AirVenture, and it's a good reason if you've never been to Oshkosh to go to Oshkosh this time. So lots of speakers. We'll have a hydrogen session, lots of viewpoints from government, industry, even academia, lots of developments, and this will be a real showcase. We have about should be about 200 some people in person, and we also have a virtual connection if you don't want to go to Oshkosh.
Awesome. Thank you so much, Mike. And for those of you that are kind of new to some of you came from the hydrogen space and are new to the aviation space. So Mike mentioned AAM, which is Advanced Air Mobility, which is the eVTOL flying car, although I know, Mike, you hate that word flying car, but flying taxi, air taxi, basically this, boom that's happening in aviation. So the AAM, Advanced Air Mobility, is the umbrella that sums it up. So this will be the biggest AAM event at Oshkosh. So I can't wait to see you there. Next up, we have Flying High. Flying High is HYSKY's annual hydrogen aviation event. It's the world's largest hydrogen aviation event. It's September 3rd through the 5th in Las Vegas, Nevada at Caesars Forum. We are so excited for this event. It's co-located with the Commercial UAV Expo. I always see tons of friends at the Commercial UAV Expo, so I'm so excited to be partnering with Commercial UAV Expo on this event. If you haven't registered, make sure and register ASAP. And if you're interested in speaking, we may have a couple slots open still. If you're interested in exhibiting, you can email me directly, or you can email Angela at HYSKY.net. Rishav, if you could put her email in the chat, that would be awesome. And so there you have Advanced Air Mobility again. So we'll be having tons of advanced air mobility stuff there, hydrogen hubs, zero emission aircraft, hydrogen airports, networking, and of course the hydrogen aviation course, and lots more like demos and pilot lessons and all kinds of cool stuff. So you don't want to miss this. Be there. Next up, I'm so excited to let you guys know that HYSKY and AIAA have partnered. If you're not familiar with AIAA, AIAA is the largest professional organization for aerospace and aviation. And we've partnered with AIAA to bring you the Advanced Hydrogen Technologies and Design course. This course is October 8th through November 7th. And there is a discount code for AIAA members. I know some of you are AIAA members. Rishav, if you want to, you mentioned, I think you had a code that you were going to put in the chat. Cool. So yeah, make sure and register for that. It's online. And the schedule is down here. It'll be Tuesdays and Thursdays from 1 to 3 p.m. You will be able to purchase the course after it. It will be recorded. But I highly recommend you attend it live. You're definitely going to get the most out of it attending it live. You'll be able to interact with the instructors, one of them being me, another one being Matt Moran from NASA, and more. So you'll be able to have that interaction, get a better experiences. But if you can't attend on those dates, you will be able to purchase it after. So next up, please help us spread the word of HYSKY. Like I said, we're a 501c3 nonprofit, and everything that we do depends on you guys helping us spread the word, reposting, sharing our materials, attending these webinars, and just engaging. We depend on grants, donors, and participation. So this is a company brochure that we just published, and I'll actually give you that link as well. I don't want to copy that. It's just going to be easier for me to do this. So, consider making a monthly donation. It could be $10. It could be $10,000. Everything counts and everything makes a difference. So, yeah, please consider doing that. That helps us a lot. And huge thanks to last month's speaker, Matt Williams from CARB. I had to miss that one because I was in the hospital with my daughter. She was having twins, but the twins are here. They're 4 weeks old yesterday and they're doing well. So thank you for that. And I believe that is it for me. And now I'm going to let Rishav take the stage.
Hey everyone. Where is my video? Oh, seems that I can't start my video. So welcome to the 55th monthly episode of HYSKY Monthly. Last month was a terrible time. I was doing a so this month we're gonna do it even better. So let's take a group picture first. Danielle, can you
Yep.
share this so we can have all of them in gallery view? Everybody, please turn on your cameras. Here we go. Amazing.
And just say cheese and smile for as long as you can. Oh my gosh, Mike, I'm jealous.
Nice.
Come on, don't be shy. Turn your cameras on. We got about half of you. You can even be in your PJs. We don't care. Just as long as you're clothed, don't be inappropriate. But we have people joining from all different time zones. So you don't have to be in your Sunday best for this picture. We just want to see your faces.
All right.
Say cheese.
One more time. All right. I think we're there.
Awesome.
Great. So welcome everyone once again to HYSKY Monthly. Today we have Bav Roy, and he's solving the hydrogen liquefaction problem. And Bob is a co-founder and COO at Verne. or Verne. I don't know how to pronounce that, but Bav will come online in a few minutes and he'll correct me if I'm wrong. Bav grew up in Sydney, Australia, surrounded by the Australian bushland, where he developed a deep connection to nature and its conservation. He studied renewable energy 15 years ago and began working in early solar photovoltaic industry, designing and maintaining solar farms for industrial customers. He then swapped his hard hat for a suit, worked as a management consultant at BCG. There he advised executives in energy production, electricity and gas utilities, fuel stations on a range of strategic and operational challenges. In 2019, Bav moved to California for an MBA at Stanford, and he wanted to find pathways to maximize his impact on climate change. Through this program, he met his co-founders, Ted and David, and came to appreciate the potential that hydrogen could have if the storage and distribution challenges were solved. So this was the genesis of the company, Verne, which is bringing breakthrough high-density storage and distribution technology to heavy-duty transportation application. And this includes trucking and aviation. At Verne, Bav leads the company's operations, including commercial demonstrations and manufacturing. He has built and led teams for demonstrating the first 1 megawatt-hour heavy-duty cryo-compressed hydrogen system, and for demonstrating Verne's first cryo-compressed hydrogen fuel cell vehicle. He's now working with leading truck manufacturers, fleets, and infrastructure providers to demonstrate the first pilot cryo-compressed hydrogen truck system. So Bav, welcome to our HYSKY Monthly, and up to you.
Great. Thank you, Rishabh, for the introduction. Can everyone hear me okay?
Yep.
Thumbs up. Okay, great. And Danielle, congratulations on the twins. That's huge news. Thank you everyone to the HYSKY community for tuning in today. It's a pleasure to speak with you about what Verne is working on. And we're named after Jules Verne, who talked about hydrogen-powered shipping actually well over 100 years ago. So he was a bit of a visionary. But let me see if I can get my presentation sharing here. All right. So what Verne focuses on is high density hydrogen for heavy duty transport. A little bit about me. Rishabh already gave a bit of intro, but yeah, I lead a lot of the operations and early commercial demonstrations at Verne. Originally worked in the solar industry in Australia, then as a management consultant before moving over to California to focus on bringing novel solutions to climate change, and saw a lot of potential for hydrogen to have a role across the landscape, but especially within transport, as I'll talk about today. So everyone on this call is very excited about the role that hydrogen can play within aviation. So this is a third-party report by the Air Transport Action Group. They expect that hydrogen will provide 33% of aviation energy in 2060. So it is a little far away, but we're talking a pretty significant part of the aviation energy mix, well above electricity, but not quite as much as SAFs here. And in order to transform the aviation industry to actually run on hydrogen, we're gonna need a massive transformation. So on aircraft development, it's estimated approximately $10 billion is going to be required to develop new aircraft that run on hydrogen. On the infrastructure side, $30 billion are going to be required to prepare the airports to actually fuel, to safely fuel these aircraft. And then, of course, we've got to get the fuel to the airport. So the hydrogen fuel delivery is another $10 billion. So across these three categories, we're looking at $50 billion to really stand up the hydrogen aviation industry. Of course, each of these are massive. However, there's something that's even bigger. So hydrogen liquefaction is going to require about $50 billion. So as much as all three of those previous categories combined, right? So if we think about the aircraft development problem, the infrastructure problem, and the fuel delivery problem, the cost of all of those is expected to, in total, be the same as the cost of liquefying hydrogen at scale for aviation. And that's simply because the process of hydrogen liquefaction, it's a very mature and great technology, but it is expensive. It is not cheap. It provides a lot of CapEx and OpEx that really impacts the economics of hydrogen aviation. So to start with the operational costs, so hydrogen liquefaction, most liquefaction plants today are about 12 kilowatt hours of energy required to liquefy a source of hydrogen gas. And that's after it's been produced, not accounting for the energy required to produce the hydrogen. Just to liquefy the hydrogen, it takes about 12 kilowatt hours of energy, because we need to take that hydrogen molecule all the way down to negative 253 degrees Celsius. So for 1 kilogram, it takes 12 kilowatt hours of energy, and then you get about 15 kilowatt hours of energy, of usable energy on board an aircraft for the engine or for the fuel cell. So already we're starting off with a pretty tough equation, even when we assume the energy required to produce that hydrogen is free. And then on the equipment side, each liquefaction plant, and here we're showing a 30-ton per day liquefaction plant built by Air Liquide. They're big industrial plants. They're not easy to build out. They take hundreds of millions of dollars, many years to build. And so to think about how this is going to scale at a global level is required for aviation, we definitely have our work cut out for us. We'll have to think about how we get liquefaction plants in every continent, in many cities, to be able to supply liquid hydrogen to the airports. And so what Verne does is we solve the liquefaction problem. So we think about the status quo that the industry is planning for, which is fueling aircraft using liquid hydrogen. That's going to cost about $50 billion. However, with cryo-compressed hydrogen, we can bring that cost way down to a more modest $20 billion, providing $30 billion of savings that can be used for some of the other challenges on aircraft development, infrastructure, fuel delivery, or even production. So what is cryo-compressed hydrogen? So let's take this back to the basics of thermodynamics. So here, thermodynamic chart of hydrogen. We've got temperature on the x-axis, hydrogen density on the y-axis, and then lines of constant pressure or isobars here. So compressed gas, which is where a lot of the current hydrogen aviation prototypes, what they use for storage, they store hydrogen at 350 or 700 bar pressure. And ambient temperatures. This provides moderate densities. But then now the industry is working hard towards a liquid hydrogen future, which is in orange here on the far left. So that's at cryogenic temperatures, so roughly negative 253 degrees Celsius. And you do get to decently higher densities than compressed gas. However, you've got a very narrow band of temperatures to be able to store that hydrogen in, and it takes a lot of energy to get it that cold, as I mentioned before. So what Verne is doing is this blue region here. So it is it's technically a supercritical fluid, but it's easiest thought of as a cold compressed gas. And that's this blue triangle here. It is higher density than liquid. It is warmer than liquid. and single phase, and that it's just a cold gas. So there's two ways to get to this really high density state. One is using a source of delivered liquid hydrogen and using a standard commercially available cryo pump to get to this state. And that's going to be applicable for many industries, for example, in trucking, where it's pretty straightforward to have a liquid hydrogen distribution network. But the other path that we've developed is a way to chill a source of pressurized gas. So you can pressurize the hydrogen gas to approximately 350 bar, and then chill it to get it to the cryo-compressed state as well. And that new process that we've developed completely avoids the liquefaction supply chain, so saving a lot of energy and a lot of cost. And so this is potentially quite interesting for aviation, where of course the fuel is a pretty big part of the total cost of aviation. And so just to summarize, for cryo-compressed hydrogen, it is the highest possible density, and it is compatible with both the compressed gas supply chain as well as the liquid supply chain, depending on what is appropriate at each airport. So we think about what's important for aviation. So one is the fuel density, of course, and the other is the fuel cost. So we look at liquid hydrogen as a comparison, and we think about usable hydrogen density here. So we see, and that's a function of the amount of hydrogen you can actually store in a vessel at the right pressure and temperature, as well as the amount you can actually empty these liquid storage tanks. So liquid hydrogen, it has about 45 grams per liter of usable hydrogen density. In contrast, cryo-compressed hydrogen, when you supply it from a gaseous hydrogen supply chain, so using that chiller technology that I mentioned earlier, you are able to get to slightly higher densities than liquid hydrogen, but you benefit from major savings on fuel cost, because you're not going anywhere near as cold as liquid hydrogen temperatures, and you avoid the equipment of a liquefaction plant. But as I mentioned, you can still use the liquid hydrogen supply chain if you happen to have a great low-cost supply of liquid hydrogen. And so you fill the same cryo-compressed hydrogen storage systems on board aircraft using a source of liquid hydrogen supply, you are able to get to actually much higher usable densities, because simply put, that cold gas is even colder if you start from liquid hydrogen than if you start from gaseous hydrogen. So you're able to get to much higher usable densities than cryo-compressed from gas and also than liquid, but you don't get any of the fuel cost savings that you would if you skipped the liquid hydrogen supply chain. And so what this means is aircraft developers now have flexibility. They can design for cryo-compressed hydrogen storage on board, knowing that in every scenario it's going to be the highest usable density, and in supply chains that have gaseous hydrogen supply, the aircraft can benefit from lower fuel cost. And for supply chains that have liquid hydrogen supply, the aircraft can benefit from even higher usable density. I thought I'd touch briefly on the concept of usable density, because often we hear that liquid hydrogen is the actual density is 71 grams per liter. That is true for liquid hydrogen stored at 1 bar. The challenge is you can't actually store liquid hydrogen at 1 bar on vehicles. It often is stored at slightly higher pressure, and what that does is that brings down the max fill density to unfortunately lower densities than 71 grams per liter. And so here we see 700 bar gaseous hydrogen, liquid hydrogen, subcooled liquid hydrogen, and cryo-compressed hydrogen. And light blue is the max fill density. So this is the maximum hydrogen you could put within a storage tank. And so we see liquid hydrogen, subcooled liquid hydrogen, they do have substantial improvements relative to 700 bar. However, when we think about the amount of hydrogen you can actually get out of that storage tank, it is not quite as high as we would like. If you look at 700 bar, the usable density is pretty close to the maximal density because that system is already supplying hydrogen at pressure as required by a fuel cell or an engine. Cryo-compressed hydrogen, in contrast, as I mentioned, it is just a cold compressed gas. And so what that means is it has even higher densities than liquid, and a lot of that is actually usable. And so we are able to get to usable densities even higher than the maximum fill density of liquid hydrogen subcooled. And so generally just the way we think about it is about 80% usable density, higher usable density at 700 bar, and 40% higher usable density than subcooled liquid hydrogen. And here this picture is a early prototype that we developed, a 4-tank system. Each of those tanks is about 2 meters long and 700 millimeters in diameter. And each of them store about 30 kilograms of hydrogen. We're going to get to much higher densities with some of our next generation systems. So we often think about these systems as storing cold compressed gas, and that often it creates the question of, well, that sounds pretty expensive. It's got to be pressure compatible. It's got to be temperature compatible. However, because we're able to get to such high densities, and we're only sticking to 350 bar hydrogen, so it's a lower pressure than what, say, a Toyota Mirai has today, we actually able to get to lower storage costs than even compressed gas. So we expect to get about 50% cheaper than 700 bar. And that's simply because each storage tank has such high density that you have fewer tanks to store a given amount of hydrogen. There's less carbon fiber, less valving to store the same amount of hydrogen. We verified this with our own internal analyses as well as some third-party analyses from Argonne National Lab and a couple others. So what does Verne do? So we have 2 products. One is the cryocooler to compress and cool hydrogen to increase that density. And so here on this pallet actually is a 1 ton per day cryocooler that we tested in Ariel, Colorado. And then on board vehicles, we provide the storage systems. So the vessels, the control systems, the balance of plant heat exchangers to store hydrogen at that highest density. And that's all with passive insulation, so insulated storage tanks. And so the benefit for aviation is that on the cryocooler side, rather than these massive liquefaction plants that will take many years and hundreds of millions of dollars to get off to get set up, instead these cryocoolers can be developed. They're efficient, low cost, and modular. So this can be done at 1 ton per day. It can also be scaled up. And then on the storage side, we've got these high density, lightweight storage systems that are supply pressure, so they're compatible with ICEs as well as with fuel cells. So this is a new state of hydrogen, right? We've got gas, we've got liquid, we now have cryo-compressed. Yeah.
Sí. Yeah.
So is there a
Please
question?
mute everybody while Bav is presenting. Thank you.
Thank you. So yeah, it's a new state of hydrogen. Of course, this is a massive opportunity, right? There's hydrogen trucking, aviation, off-road distribution, many applications for cryo-compressed. Our company started 4 years ago. We're trying to pick where we think we can have the biggest impact for the soonest. And so we have to focus a little bit. So the way we've staggered our kind of approach to various markets is to first focus on trucking and distribution, where we think we can more easily demonstrate the technology at scale, and then use learnings from those 2 markets to then translate over to both the off-road segments as well as aviation, such that by the time those markets are even more mature, we've already got a great track record from trucking and distribution. So I'll now touch briefly on on some of the work that we're doing in trucking and distribution, and how that kind of leads to some benefits in aviation. So as I mentioned, two applications in near term: trucking and hydrogen bulk distribution. So for onboard storage on trucks, so we're able to maximize the usable hydrogen on board. We're able to, because we're at such high density, we can store enough hydrogen exactly where the diesel tanks are on trucks today. And so we'll actually be demonstrating the first ever cryo-compressed hydrogen truck later this year. We've already powered a fuel cell vehicle with cryo-compressed hydrogen. And then as I mentioned, we're working on powering an engine this year. These storage systems are compatible with both the liquid hydrogen and gaseous hydrogen supply, as I mentioned earlier. And that's really important for truck fleets that don't want to adopt a fuel unless they know that they'll have fuel security, that they know wherever their tractors go, they'll be able to actually fill up. And that's one challenge that we saw with LNG in North America, and why it didn't really take off. And then low boil off at both the station and vehicle side. So today we hear the liquid hydrogen supply chain, unfortunately, just due to the tricky nature of liquid hydrogen and it needing to be stored at such cold temperatures, does suffer from a lot of boil off losses as hydrogen is produced, transferred over to trailers, and then moved from trailers to stations. And so with cryo-compressed hydrogen, we're able to minimize that boil off throughout that supply chain. And on the distribution side, so here is it's essentially a trailer product along with the cryo cooler. A combination of those two things allow you to minimize the total cost of delivering hydrogen for specific distances and scales. So we're not kind of saying that cryo-compressed hydrogen is the silver bullet here. Liquid hydrogen distribution is going to have a pretty big role, as is gaseous hydrogen. But it's kind of a sweet spot of distance and scale where cryo-compressed hydrogen distribution can really be the cheapest option, particularly as you're able to minimize that upfront capex of using a cryo cooler rather than a liquefaction plant. So within trucking, we're really excited about the momentum in trucking. So all of the heavy-duty truck manufacturers in the US and Europe have some form of a fuel cell and hydrogen combustion engine program. And so that's already, we're talking like 100% of the market pretty much has multiple powertrains for hydrogen. And then we're excited to see some newer OEMs as well in Hyundai and Nikola kind of moving a little faster than the OEMs. And then, of course, there's many fuel cell suppliers, so Toyota, Cummins, and then kind of a new feature of the last few months, to be honest, is on the engine side. That there's been a lot more focus on how hydrogen engines can also be adopted in trucking to bring down the vehicle cost in particular, whilst fuel cells are still kind of early in their technology maturity and they're still pretty expensive. So what can cryo-compressed hydrogen do for trucks, just to make it very tangible and real? So what I'm showing here on screen right now is an existing hydrogen truck using 700 bar compressed gas storage. So here in this backpack behind the cabin of the truck, they have 6 700 bar tanks. And this vehicle is able to go about 450 miles range, which is about half of what a diesel truck can go today. And the truck weighs 21,500 pounds. Again, for comparison, the equivalent diesel truck weighs about 16,500 pounds. And so that's a meaningful hit on the payload that truck can carry. So that's less revenue for the fleets. So this is 700 bar truck. With cryo-compressed hydrogen, we're able to provide substantial benefits to either increase the range or lightweight that truck. So starting with a long range option. So in that same region, we could store 4 tanks to about double the hydrogen on board and double the range without impacting the weight. And so what that means is that that can halve the infrastructure requirement for trucks, because they can always come back to fuel at their same home base. And then on the lightweight option, we're seeing a lot of traction for this, particularly in drayage and other applications. That we can, it's completely avoid this backpack. Instead, store hydrogen in 2 tanks, either side, saddle-mounted tanks, to get to at least about 450 miles or more range, whilst bringing down the weight and shortening the wheelbase of this truck. And that can potentially double the fleet margins for payload-constrained fleets that already have pretty tight margins on their operations and really suffer from any hit to their payload carrying capacity. So this is a 3rd-gen system that we're working on. So this stores is designed to sit behind on the side of a truck. It stores about 40 kilograms. It's designed to be a direct swap in with existing hydrogen storage. It includes the storage vessels, the balance of plant, signal receptacle, heat exchanger, all the pressure management equipment, as well as the controls and electronics. So really to make it an easy one-for-one replacement without needing to think about what does a fuel cell or engine see, because the fuel cell engine will see exactly what they see today if they have compressed gas storage on board. So of course, we've talked a lot about the on-vehicle side. There is an established liquid hydrogen network in North America. We also want to maximize our compatibility with that. So here, what I'm showing on screen is the existing liquid hydrogen to compressed gas kind of supply chain. So some of the new hydrogen stations that are being built, they'll have a liquid hydrogen tank, a cryopump that essentially converts liquid hydrogen to compressed. Then there's a vaporizer to heat up that cold compressed gas, buffer storage, and then a dispenser hose and nozzle to fill these compressed gas trucks. And actually in this dispenser, you'll have a chiller unit to chill that hydrogen to -40 Celsius to prevent the tanks from overheating. So funny enough, in this process, you actually already get to compressed hydrogen immediately after the cryopump. However, because there's no technology, there hasn't been any technology to store cryocompressed hydrogen gas, the hydrogen is heated up, and kind of that really high density and that energy, that cold energy, is wasted. And so it's quite unfortunate. So what we're doing is we're working with a number of station developers to ensure they can essentially dispense cryocompressed hydrogen as well. And it's actually really easy to retrofit. You just bifurcate the line and just keep that hydrogen cold out of the cryopump. It's already in the perfect state to fill these trucks. And so we've actually recently announced some testing that we've been doing on the nozzle and hose for cryocompressed hydrogen. The nozzle and hose for cryocompressed hydrogen. And so all we need to do is out of that cryopump, keep it cold as we fill these trucks. And I guess the same thing applies for aviation, in that if, as we expect there will be, if you're already planning to have at least some of this equipment, we could just reuse the same liquid hydrogen tank, same cryopump to fill these trucks. Fill cryocompressed aviation. And of course, like I mentioned, this is the liquid hydrogen side. There's of course the low cost alternative if you want to use the cryocooler to just bring down that fuel cost by using the gaseous hydrogen supply chain and cryocooler that will chill that pressurized hydrogen. So in summary, there's kind of multiple ways to fill any sort of cryocompressed storage. You could use the liquid hydrogen supply chain and a cryopump. You could use the compressed gas supply chain and a cryocooler. And worst case scenario, these are 350 bar pressure vessels. If for some reason you were stranded, you had no source of cryocompressed hydrogen, you could fill with 350 bar hydrogen, which is not something that we would recommend because it's it's not as efficient as even a standard 350 bar tank, because you'll then have extra insulation and other components. So to make this really real, we're demonstrating the first cryo-compressed hydrogen truck this year, and we'll start to invite external parties to actually see it early next year. And this is actually the truck that we're working on. So it's a Volvo diesel truck. We're actually working with a third party to blend cryo-compressed hydrogen into that existing diesel engine, just as a more cost-effective way to demonstrate our storage technology. And then what we're also demonstrating is our mobile refueler. So this will take a liquid hydrogen supply and here's a cryo pump, so we'll cryo pump it into this truck. And so this will kind of show both like the truck performance as well as the simplicity of the fueling process. So as a summary, in the near term, we're mostly focused on trucking and distribution, but we're excited about how cryo-compressed hydrogen can have a role in aviation. And then on the distribution side, briefly, what cryo-compressed hydrogen trailers can be filled by is, one, using the liquefaction plant. You've already invested in a great liquefaction plant. You can still fill these trailers using that cold compressed gas. But then if you don't have a liquefaction plant, you can instead put the cheaper compressor and cryo cooler to still fill cryo-compressed hydrogen trailers. It just won't quite be as cold as if you use the liquid supply chain. And so each of these had their own benefits. So using cryo-compressed hydrogen trailers with liquid supply, it means you can reuse the equipment. You have a lot less losses during transfers, and it's modular trailer capacity. You don't need to just deliver one big liquid hydrogen tank. You can scale it down as required. And on the cryocooler side, as I mentioned, it's much lower densification cost. You can roll out your densification equipment in a much more modular way, and you still benefit from having low or no losses during transfers. Okay, so just a bit about our team. So you got myself, the Chief Operating Officer, on the call. We're also led by our CEO, Ted, and our CTO, David. And then we've also got some experts from the hydrogen industry. So Kaushik Malik, who's the former CTO at Steelhead Composites. He's really been a pioneer of pressure vessel technology over multiple decades. We've got Vincent Helwan. He spent decades at Air Liquide in cryogenics, and then developed a helium cryocooler at the Stanford Linear Accelerator. And then recently, Alex Grab has joined us from Nikola. So he developed the onboard hydrogen storage systems at Nikola, and previously used to work at Luxfer. And then on our advisory board, we've got Tom Linebarger, the former CEO of Cummins, really helping us think about how do we can develop a trusted brand and manufacturing process similar to what Cummins has, as well as, I'll mention, Salvador Seves, the original inventor of cryo-compressed hydrogen and former group leader at Lawrence Livermore National Lab, where we've done a lot of our testing to date. We're grateful for a lot of the funding we received from Breakthrough Energy, RPE, Department of Energy, and then recently we got a US Army grant as well. And then private capital. So we've got investments from United Airlines, Trucks, as well as Amazon and Caterpillar. So just to recap, where this will become very real is we'll start to be able to show people the first cryo-compressed hydrogen truck. For those that are interested, we'd love to be able to have various industry stakeholders come and see the technology, see how simple the fueling process is, and see the high densities. Thank you. And now would love to take any questions.
Thank you so much, Bav. That was fantastic. I kept having questions, and then you would answer them on the next slide. I was hoping you could share your screen again, because I wanted you to go back to the chart where you compared like this is currently the process and then this is what we're doing.
Mhm.
Could you go to that slide? And
Yeah.
I have a question about that one.
Is it this slide?
Yes. So
Mhm.
you mentioned that, well, it seems very obvious that you would do it the way that Verne is doing it. And you mentioned like it hasn't been done like that because the technology didn't exist, I think, on board the vehicle. Why was that technology not existing? Is it complicated and nobody had done it? And is that sort of your secret sauce? Or did people just not think about it?
I'd say more the first, and that it is challenging to develop the technology to store hydrogen at pressure and temperature, and cold temperatures. Like there's an established industry for cryogenic liquids. There's an established industry for high pressure systems, and there's almost nothing that can do both. And so it has been historically quite challenging to store hydrogen in this state. But that's where a lot of Verne's secret sauce comes in, is that we're able to do so in a way that is cost effective and manufacturable at scale.
I see. Well, I hope I get an invite to your demonstration. Would love to bring some aviation folks with me to see it. I think this is a game changer. There was
Absolutely.
one more thing I wanted to ask you. And then we'll get to the questions in the chat. But what do you say to, the majority of hydrogen aviation industry? It's not quite an industry yet, but I guess I should say group and developers. There's a really general consensus that it has to be liquid hydrogen on board the aircraft. And you explained the density of cryo-compressed. What do you say? Do you get that comment a lot? I hear it all the time. What do you say to that?
Well, I guess I would start by agreeing that it has to be really high density, right? I think that's why everyone suggests that it needs to be liquid on board, is because compressed gas will just won't get there, right? It just won't work for aviation applications. I guess I would say let's look at the economics of aviation today. Fuel cost is potentially the biggest driver of the economics. And if we look at this, the cost of liquefaction, it is going to come down. There's going to be a limit as to how far it can come down. And if it's anywhere near the cost of what it is today, I'd love to see how hydrogen aviation can be economical. So instead, what cryo-compressed can offer is slightly higher densities than liquid, without the major fuel cost penalty.
I love that. I'm really excited to work with Verne and see where this technology goes. It seems really smart. Okay, so the
Thank you.
first question that I see was, let's see, I'm scrolling through the chat. Sarah, if you want to unmute and you can turn your camera on if you'd like. You can ask Bob your question. Sarah Mitron, I hope I'm pronouncing that correctly. I don't know if Sarah's still on.
Oh, she is at the airport.
Well, her question was, what TRL are you at? Questions, I should say. Are you producing already? Do you require special storage?
Yes, so we developed a special storage, right? Like that's one of Verne's products, is the storage side, and the other is the densification side. So on the storage side, we're at TRL, approximately TRL 5 right now. And we're working to take it to TRL 6 next year and 7 the year after. And this is for the trucking application. Will take a little longer to replicate that in aviation. And on the densification side, it's late TRL 4, I'd say right now. And then we'll be demonstrating TRL 5 this year.
Nice. That's exciting. Next up is Arnie. Arnie, would you like to unmute and turn your camera on and ask your question? And while we're waiting, I'll just encourage you all to not be shy because these we have seen so many partnerships come out of these webinars, and it usually happens at the end when we're doing the Q&A. So don't be shy. Let's please go in order. I don't see Arnie unmuted, so unless Arnie starts talking, I'll ask his question for him. What pressure do you store the cryo-compressed H2? I think you did talk about that.
Yeah, so we fill our storage vessels up to 350 bar pressure. The benefit of that is we're able to really minimize the carbon fiber relative to 700 bar and reuse a lot of the same equipment that has already been used within the 350 bar industry. And then whenever you heat up the hydrogen, whenever you store the hydrogen, it heats up over time, and it increases in pressure. And so we have pressure management capabilities that prevent overpressure beyond 400 bar.
Okay, yeah, that's I also thought it was really interesting that because I was thinking I want to ask about infrastructure, but I thought it's brilliant that you're working with the refueling stations already. And what does that look like going, beyond the state of California?
Yeah. So right now we're really looking to help the station developers design their stations such that they can easily add cryo-compressed dispensing capabilities. And that's not unique to California, right? Like some of the first demonstrations will be in California, but then actually our next one will most likely be in Alberta. So we actually won a sizable grant there to demonstrate the dual fuel engine truck and a mobile refueler within Alberta. So we're really going wherever the fleet interest and the truck manufacturer interest takes us. And we're finding that we're able to either provide a mobile refueler to those applications or just retrofit some of the local stations. And of course, most of the stations today are in California, but we're excited for that to roll out nationwide.
Yeah. Thank you for that clarification, and sorry for the background noise. I don't know if you guys can hear that. Christopher Hedrick, you're up. You are unmuted, it looks like. Please ask your question.
Yep. We produce low-cost true green hydrogen. Our first facility is going in at Red Bluff. Our second facility is at Tampa. We're concentrating on heavy transport trucks in California. Can't really make those numbers work anywhere else. The trucks are just too expensive. My question is, from an installation perspective, we're doing 12 tons a day at our facility in Red Bluff, California. I'd love to discuss this with you guys and see if this is something we looked at liquefaction, and the numbers are just obscene. You cannot make those numbers work, and it doesn't matter who you are; they just don't work. So if you guys can really do it at this number, we produce our own electricity too, so we don't connect to the grid, so we're not hostage to the same excessive electricity rates that everybody else is. So we'd love to have that conversation and see if there's in Tampa, we're doing the Port of Tampa. So we're looking at shipping, and then we actually use our syngas to make electricity as well. If you can do hydrogen, you should certainly be able to do our syngas before we purify it. Would love to have that conversation with you guys.
Absolutely, yeah, and definitely can empathize with that high cost of that liquefaction plant. We're getting a lot of inquiries because people see that it's just not cheap to build one of these, and so yeah, would love to chat, Chris.
Yeah, absolutely, sounds great.
I'd also love to chat, Christopher. I'll probably reach out to you separately. I don't know if this is your first time here.
No,
okay.
Yeah, I'm here. I'm generally here every month.
Have we talked before?
We have.
I'm sorry. I talked to so many people. But yeah,
Well,
I don't know.
I
Go
used
ahead,
to
sorry.
be H2 Energy Group. We just we're converting over to Victory Clean Energy now. So H2 is how everybody knows me.
Okay, gotcha. Yeah, I definitely want to follow up on that. Okay, next up we have, I want to make sure I don't skip anybody. We've got Stephen. Stephen Lay, are you here? Would you like to ask your question?
Yeah, can you hear me okay?
It's kind of quiet.
Let me turn. How about this? Can you hear me better?
Yes.
Okay. Yeah, I was just kind of curious. Obviously on aviation, we're very sensitive to volume and weight. A lot of things I've seen from Airbus Industries, looking at aircraft, these tanks are fairly large and pick up a lot of revenue producing volume on board the aircraft. And I'm really curious about really the economic or actually the economic viability of using gas, hydrogen gas form on board aircraft versus in a solid state form. So I'm just kind of curious, is there any discussion with any aircraft OEMs or developers in being able to use hydrogen as a fuel source in a non-gaseous state?
Just to make sure I was able to understand that correctly, was it a question about the size and weight of the storage on board?
That's part of it.
And
Yeah,
what was the other part? Sorry, it's a little hard to hear.
Part two is to been any discussion of being able to have hydrogen on board the aircraft in an other than a gaseous state, like in a solid state form.
Got it. Yeah, so I can answer the solid state form first. So most of the kind of solid state hydrogen storage methods, they actually are decently heavy. And so for aviation, that can be a challenge where weight is, of course, quite critical. But the great storage methods for other applications, for example, stationary storage, potentially at the airport or other applications. And then yes, completely hear you that space and kind of weight of hydrogen storage, it's nowhere near as good as SAFs or even jet fuel. It is it's kind of an uphill battle. It's just if you are going for zero emissions, then you have to either go with SAFs, hydrogen, or batteries. Batteries a little too heavy. And then SAFs, the fuel costs are always going to be higher than hydrogen. And so it's really, in Australia, we say horses for courses, and that there'll be some applications that within aviation that will go SAFs, right? You'll need just so much energy on board that you'll have to go that higher density and pay that fuel cost penalty. But where you are able to take the density hit by going with either liquid or cryo-compressed hydrogen storage on board, you can then benefit from the cheaper fuel.
Thank you.
Thank you for the question, Stephen. And happy to connect you to if you didn't fully hear it. It was kind of hard to hear the question. So there's a lot of comments. I'll just kind of summarize what I see a lot of people saying in the chat are thinking about like the other use cases, not just in transportation, but with grids. And Ashley mentioned the Texas grid and the brutal winter. And I live here in Houston, and we also have brutal summers. Our power has went out, I think, 4 times in the last month from thunderstorms and almost tornado conditions. And it's sometimes just a little wind. There's a lot of reasons, but mainly when it's hot, when it's really hot, we're all using the air condition and the grid can't support it. So I'm going to summarize a lot of these comments and say, are you all looking at the energy industry and this use case for grids?
Yeah, that's a great question. To be honest, we haven't. We're really trying to stay focused to first deliver on trucking and distribution. like that alone is like each of those are massive markets for us, and we're trying to do what we say we'll do and execute well there before then expanding to some of these other great applications. And so I'd ask us to kindly just wait for us to first get rolling in trucking, and then we'll extend the technology to some of these other applications. Yeah.
I love it. It's a great answer. This question's for me. How much does that Gen 3 tank weigh full?
Yeah, great question. So the Gen 3 tank, you know what? I actually don't have the number off the top of my head, but it's definitely not designed for aviation in that it can be made much lighter. Generally, the levers that you have to pull for designing these systems are the cycle life, the amount of hold time for this cold gas, and kind of the safety factor. And all of these have been designed for trucking. And so what that means is like very long cycle life that will last well beyond the truck's lifetime, whole time of like 2.5 days. And the safety factor is appropriate for the automotive and trucking world. And so I think generally with all of that, we're looking at about approximately 10 weight percent for cryo-compressed in trucking. And then for aviation, it'd be a slightly different design, but you could get, of course, much higher because you'll be able to remove some of those constraints, not all of them.
Right. Okay. Awesome. Love to hear what that weighs. Sarah had another question. I don't think she's here. Sarah, if you are here and you missed the unmuting last time, you can unmute. But she's asking, will you be operating in, or will you be operating out of San Francisco? I think you kind of touched on that already.
Yeah.
But yeah.
Yeah, so our headquarters is in San Francisco. We actually got kind of small scale manufacturing there. And we work with partners actually across the US for some of the more capital intensive parts of manufacturing. But so far we do all of our building and assembly in San Francisco, and some of our testing in the broader Bay Area at Lawrence Livermore National Lab and elsewhere.
Awesome. Hugh Edwards, are you, I think you might have had the same question I did. Hugh, I'm just going to say this because but he says, what is the weight or gravimetric efficiency of the CCH2 tanks compared to liquid hydrogen tanks? Not exactly the same question, but a weight related question.
Yeah, so at the truck scale, it's approximately the same weight, gravimetric density, or approximately 10 weight percent thereabouts. For aviation, if you need larger vessels, generally what you'll see is the larger the vessel, then liquid hydrogen will start to have an advantage. It's just simply put, liquid systems scale much better than pressure systems. And so if you think about massive storage systems, then liquid hydrogen will be the lighter solution. And so as I mentioned, I can't yet quote a gravimetric number for aviation. It will be higher than 10%. And most likely either equivalent or slightly lower than liquid hydrogen systems.
Mm-hmm. Thanks. Kramer, you're up. And just a reminder to folks, when you do ask your question, introduce yourself, say what company you're with, what you're working on, just to provide a little context.
Hey, Bev, great presentation. And Danielle, congrats on the kiddos. Questions for you. Just a couple quick. From an energy standpoint, if liquid is stored at the airport or at the point of use, how much energy does it take to go from the liquid to the cryo-compressed? And then the second question is, and this might show my ignorance on cryo-compressed, so I apologize ahead of time if it does. Can you get a bleed-like failure with cryo-compressed?
So I can answer that second question first, is no, you can't. That's because it's already pressurized, right? And so you just can't, there's just no way that you'll get that sudden bleed event.
Even in a loss of containment?
Yeah.
Okay.
It's equivalent to just a cold gas leaking, right? It's just if you think about what would happen in a 350 bar pressure vessel leak, it'd be very similar to that. You actually have it's actually a little safer because it's a cold gas, you have 1/6 of the expansion energy relative to even 350 bar. And just some of our insulation, like our insulation material, will actually minimize the likelihood of any sort of impact to the pressure vessel. So we actually have a couple of safety advantages relative to compressed gas and relative to liquid. And your first question on the energy intensity. So cryopumps are actually very efficient. So the cryopump takes liquid hydrogen to either compressed gas or cryocompressed. There we're talking, I think about 0.2 or 0.3 kilowatt hours per kilogram. So really, really not much. But you've kind of already paid for the energy if you've liquefied it upstream, right? So yeah. So you wouldn't get any fuel cost savings there.
Thank you.
Yeah.
Great question. Next up is Ashley Graybill. Ashley, are you on still? And would you like to ask your question?
Yeah, I'm here. Hi, Ashley Graybill, Sensienza Design Sensors. My question is mostly in regards to the safety measures taken in regards to compressed cryo. Is it just a set of basic sensors? Is it a complex array? How are you going about making sure that people know what's going on with their systems when they have them?
Yeah, great question. So we have a number of sensors. So there'll be pressure sensors to ensure we're able to track the pressure and prevent overpressure. Similar, we have some temperature sensors to give more accurate perspective on the fill state. We technically will not need hydrogen sensors for most of our system because we have a vacuum insulation system around our pressure vessels, and so there you can even more accurately detect any sort of hydrogen leak than you can with a standard hydrogen sensor. However, we'll likely still have some anyway, just around the systems, just for extra safety. But yeah, generally looking at pressure sensors, temperature sensors, and some hydrogen sensors.
Great, thank you.
Another great question. Thanks, Ashley. Oh, Sarah's at the airport. Okay, I'm finally at that part. I was wondering why somebody said she was at the airport earlier. Juan Manuel, are you still here? If you are, you can unmute and ask your question. Juan asks, how long have you been R&D on the system? And I think I might be able to answer that. I think it's 4 years.
Yeah, so we've been working on this for 4 years, and we've now built and tested numerous systems at Lawrence Livermore National Lab, at NREL, working with a couple of different vehicle manufacturers as well. We're also benefiting from decades of work done by Lawrence Livermore National Lab as well as BMW. Both of them worked on compressed hydrogen for cars. And we've actually hired a number of the key personnel from each of those programs. I mentioned Salvador Seves, the group leader at Lawrence Livermore that invented compressed hydrogen, as well as Marcus Campich, who was the technical lead at BMW on compressed hydrogen systems. So we're just to summarize, whilst Verne's been around for 4 years, we're standing on the shoulders of giants, and we're benefiting from two massive organizations that have kind of done a lot of the early proof of concept and fundamental research for compressed hydrogen.
Yeah, and not to mention your team, which is very impressive. You guys did a great job of bringing all of the experts together for this technology. So yeah, very impressive.
Thank you, Danielle.
Yeah, you're welcome. You bet. Tom, okay. Tom Freund, would you like to unmute? I'm not sure if you have a question or a comment, but yeah, you're up.
It's a comment. Very simple. If you go back to your chart that dealt with the when do you project that you'll transition into aviation. It's very curious because it turns out that's about the schedule, close to the schedule that Airbus has on introducing models that may incorporate hydrogen propulsion. I know you obviously you're funded by United Airlines, part of your funding anyway. Have you been in touch with any aircraft builders at all, say Airbus? Because I could see where they may be interested. There are sure the issues have to be overcome because the aviation is a different animal. But have you talked to them at all? Hello? Can't hear you.
Classic. Sorry, I thought I'd get through this without doing that. I can't disclose, unfortunately, a lot about discussions with the manufacturers. All I can point to is one of our public announcements is a collaboration with ZeroAvia to explore cryo-compressed hydrogen for aircraft and airports. We are talking to others as well, but
Okay.
unfortunately can't disclose that.
Okay, well, thank you.
Yep.
Rich Holloman, speaking of ZeroAvia, and you might have touched on this already. How does cryo-compressed compare in safety to alternative hydrogen tech? Rich, you can come on and ask that if you'd like, even though I already asked it. You can come on and say hi and introduce yourself if you like. And I'm not sure if he's still on because we're getting into the stretch of the meeting, the final stretch. But you kind of answered that, I think, already.
Yeah, happy to expand a little more. So generally we compare safety relative to compressed gas. And as I mentioned, there's generally thinking about it, it's already a safe pressure vessel, and then you have extra insulation around it that also provides a safety barrier. And then because there's a vacuum layer, you're able to very quickly and more accurately detect any sort of leak. We do have a metallic liner inside the pressure vessel, and so it also provides additional safety benefits relative to the polymer liners that are used in Type 4 pressure vessels. I won't get too complex here, but it generally Type 3 metallic liners that they leak before they burst, whereas the polymer liners will burst as they're failing mode. And then I touched on the low expansion energy. Relative to the liquid hydrogen, it's just a compressed gas, and so any sort of leak will immediately rise up into the atmosphere. With liquid hydrogen, given it's so cold, you first see maybe potentially a tiny bit of cooling before it vaporizes and leaks, and so and rises. So we haven't actually run the analysis of understanding liquid hydrogen safety on board vehicles. We're more focused on the gas as well. So but we expect it to have substantial safety benefits, particularly in a crash scenario, because these pressure vessels are designed to hold decent amount of pressure that in any sort of crash scenario, they'll be completely fine. So any sort of external impact is far lower than the pressure that they hold. Whereas for liquid hydrogen, the benefit is doesn't have to deal with pressure, and so you can design them to be a lot thinner and lighter, but in a crash scenario that then gives you less structural integrity.
Yeah, thank you for expanding on that. So I told you there'd be a lot of questions, didn't I? So we could sometimes, I think we could go all day with this. Sarah asks, how was your experience working with Breakthrough Ventures? But I'm going to skip this question. If you want to follow up with her privately, that's fine. Just because I want to keep these conversations focused on hydrogen and aviation. Lots of folks are saying it was a great presentation, very informative. And I think with that, I am going to give us 6 minutes of our day back. Again, Bob, this was a fantastic presentation. We're very excited to support Verne, and sorry that I butchered the name of your
No
company
worries.
on LinkedIn and at the beginning of this webinar. But it was really great. I'm so impressed with what you all are doing. I see you making a huge impact in aviation, and yeah, it was just truly an honor to have you on.
Thank you. Thank you so much for the time and the opportunity, Danielle. And thank you for forming this awesome community.
Thank you so much. Bye, everybody.